Okay, so now we're going to go over some reactions of amines, generally just how to prepare them. A lot of these reactions we've seen before, so this is just sort of a review of that. One of the ones that we learned about in the last chapter when we were the last chapter. No, the one before that. When we were talking about carboxylic acid derivatives and we introduced nitriles, right? So that would be, let me just get my pen ready. That would be if we took an alkyl halide and introduced it to this cyanoion, which is a good nucleophile, that undergoes an SN2 process that will put that cyano group on there. And then we can reduce that cyano group. How did we do that? With our regular reducing agent that we're used to, the lithium aluminum hydride, right? Lithium aluminum hydride is great at sticking hydrogens places. So that would be one way to go from an alkyl halide to an amine to a primary amine, right? We can't make secondary or tertiary because we need this SN2 process, which is only really efficient for primary alkyl halides. Also, a thing that's a signature of this type of reaction is the fact that you start off with an alkyl halide that's 1, 2, 3, 4, 5 carbons in this case, and we grow our carbon chain by an additional carbon in this method of synthesis. Okay, so that's sort of a telltale sign that you're using this method to prepare an amine. You've added 1 carbon from your alkyl halide. Another way that we can do this is from an amide. Okay, so if we started with a carboxylic acid, we can transform that into an amide. How did we do that? Remember, you could sort of mix in ammonia, but that doesn't really work very well with carboxylic acids because you just get this acid-base reaction. So the most efficient method for doing this is to first convert it into an acyl chloride, right? So this first step just replaces this OH group with a chlorine. Now it's that highly reactive acyl chloride that will readily react with ammonia in order to get your amide. And then we can further reduce an amide to an amine, again, just using that reducing agent lithium aluminum hydride. And in this case, going this method, you don't have any sort of a change in the number of carbons in your alkyl chain. If we want to make aniline, we know how to do that by first putting a nitro group on the benzene ring. How did we do that? That would be this nitration reaction that uses these 2 strong acids, nitric acid and sulfuric acid. And then the method that we learned about was to use some metal. Actually, the one that, it's funny how they like to add on as you go. The one that was previously told to us was zinc. Now we're going to add a few more on there. Iron is a good popular choice. Iron's really cheap, as well as tin or tin chloride in acid followed by base. That would be one way to reduce it. Another way to reduce it is using a method that we first learned about to reduce alkenes, and that's just using hydrogen gas over that solid platinum catalyst. Remember that it doesn't, although it reduces alkenes, it doesn't reduce benzene because benzene's too nice and stable. Turns out it will reduce a nitro group to aniline, right? So that would be one way to add an amine group, in this case, producing aniline. Another sort of way that we can produce amines, although we're going to see that it's quite limited, is taking an alkyl halide and just adding ammonia. A simple alkyl halide, especially this would work very well with smaller alkyl halides because you need, again, that SN2 type reaction. But remember, nitrogen can play the role of a nucleophile attacking that carbon and displacing it. And now we have this charged ammonium salt, while the remaining ammonia in solution can act as a base to uncharge that. Okay, the limitations of this is that you can't stop it. From there, your primary primary amine is going to react with yet another alkyl halide, and you're going to have the same process producing a secondary amine, and then that's just going to repeat itself, and you're going to have a tertiary amine that's produced. And that's going to go even one more step further until you get this quaternary ammonium salt. Okay. And the problem is that This tertiary amine is actually a better nucleophile than the secondary amine, which was a better nucleophile than the primary amine, which was better than ammonia. So as soon as you sort of kick these things off, it gets impossible to stop. You'll always go all the way to that quaternary ammonium salt. We'll find a use for that at the end of the chapter, but yeah, that's the one limitation in terms of this method of trying to alkylate an amine. One more method for creating a primary amine is, this is a new one for us, and this is called azide synthesis. Azide is N3, but how that looks is actually kind of crazy. You have these nitrogens, all of which have formal charge associated with it. Actually, there's two pairs on these. All of which have a formal charge associated with it. The net formal charge, notice, on this whole thing would be -1, because you have plus minus plus, minus plus minus. So add those up, those get to -1. And so that's why it's in a salt with sodium. Okay. So anyways, what this does is this azide, the sodium azide, will stick an azide group on your alkyl halide. So you have this SN2 type reaction. And then you can reduce your azide to an ammonia using either hydrogen gas over a platinum catalyst or lithium aluminum hydride, right? Again, lithium aluminum hydride, great for sticking hydrogens places. It's our go-to reducing agent, okay? Again, this is only going to produce primary alkyl halides because you need that SN2 first step. So let's take a look at what exactly that would look like. So again, I have my azide molecule. Notice that I have this net negative charge on this end, right? So this end is going to act as my nucleophile, attacking that electrophilic alkyl halide carbon, and that's going to kick off that good leaving group. So now I'm at this second step here where I have my azide on my alkyl chain. So then the reduction that's going to happen, we're going to have the hydrogen, right? When you think lithium aluminum hydride, you think hydrogen acting as a nucleophile, is going to attack that nitrogen and bump that pair of electrons onto that other nitrogen. And then what happens here is a loss of leaving group, but this is a little bit different than what we're used to seeing. We're used to seeing a leaving group take that pair of electrons with it. This does the opposite and actually leaves this pair of electrons behind, okay? So if we're following our electrons here, notice the hydrogen one on there kicked this pair of electrons onto this nitrogen. So that's satisfied its formal charge, but the nitrogen on the end is still left with a negative charge. That's going to put that pair of electrons down and then kick that pair of electrons in that bond onto that nitrogen. So at the end of the day, I've produced this very basic amide ion. Remember, this nitrogen with that net negative charge is a really good base, okay? Importantly though, why does this, usually we kind of avoid the formation of these really strong bases in our reaction mechanisms. Why does it form in this case? Well, because you have what is just about the best possible leaving group you could, which is the very stable nitrogen gas. Okay, so this is going to be something that's not only enthalpically favorable, or favorable from a free energy standpoint, I guess would be the right way to say it, because nitrogen is just such a stable molecule. It's got an incredibly low free energy. So anytime you form that, that's very favorable in that respect. But also it's going to be entropically favorable because you produce this tiny little ion, a tiny little molecule that's going to float away as a gas, right? So that's not only basically just very, very favorable of a leaving group, okay? But then we're left with this really strong amide ion. So the last thing that has to happen is the protonation of that amide ion, leaving us with our amine, primary amine. Okay, so that's one method to form another method to form primary amine. We have now another one called a Gabriel synthesis, which is good at forming a primary amine from this phthalimide molecule here. So notice this has got this big crazy thing going on. The key player, of course, is going to be this nitrogen. Okay, so you sort of activate getting this phthalimide ion by adding a base, just deprotonates that nitrogen. So then what do we think this nitrogen with its negative charge is going to be doing? Acting as a nucleophile. And so that's exactly what we see reacting with an alkyl halide in an SN2 type way. Okay. The second step here is you can either treat this with acid, and that would actually get you a sort of ammonium salt that then you just add sort of any base to that would deprotonate that. And so that's how I would get my primary amine. Or you can add hydrazine, and that will also sort of cut out that nitrogen, leaving you with your primary amine. Okay, the difference between these two, both of these would create a primary amine. The difference is really what's happening to the back end there. I'll say that generally speaking, acid is way cheaper than hydrazine. So this would probably be the more preferred method. Both of these methods, both the Gabriel synthesis as well as the Azide synthesis, are ways to convert an alkyl halide, a primary alkyl halide, into a primary amine. Okay, they both accomplish the exact same goal. We got to know them both, but in terms of like your synthesis strategies, there's not any sort of difference between the two. Again, they're both limited in the sense that you're only producing primary amines. Not only are you only producing primary amines, you're only producing terminal primary amines, right? You need to start out with an alkyl halide that's susceptible to SN2 type reactions. So the most flexible method of producing an amine, that doesn't have to be terminal, doesn't have to be primary, is this method right here, reductive amination. This is actually uses the first step of a reaction that we've already learned. So what happens when we take a ketone and we mix in ammonia under acidic conditions? Hopefully everybody remembers that this produces this imine with an I, right? So notice that I've just taken my oxygen and replaced it with that nitrogen. And then so we sort of learned about how we could go to this step under acidic conditions. We could also go the reverse direction if we had acid and water, okay? But what we're learning new is that we can take this amine and we can reduce it with hydrogen over a palladium catalyst. Our normal reducing method that we learned about works for other amines, creating other amines. And this will actually create an amine. And notice that I don't have any sort of those limitations on it being terminal. In this case, it is primary, but we'll see that it doesn't have to be, okay? So for example, the other thing that we can use, hydrogen over a palladium catalyst is kind of a pain in the butt to do. So in practice, what they actually use is sodium cyanoborohydride. Okay, so we learned about sodium borohydride as a reducing agent. It's should be kind of in the same place as in your mind as lithium aluminum hydride. It's actually a little bit weaker of a reducing agent than lithium aluminum hydride, which is why we see lithium aluminum hydride so much more. So this is very similar, this sodium cyanoborohydride, except for I've taken one of these hydrogens and replaced it with a cyano group. What that does is weaken it as a reducing agent quite a bit. And the beauty of that is that now it doesn't react with aldehydes or ketones. So all together in one flask, you can throw your amine under acidic conditions with this sodium cyanoborohydride all together in one step, and that will produce your amine, okay? So if you start out with ammonia, you'll get a primary amine. If you start out with a primary amine, you'll get a secondary amine. If you start out with a secondary amine, you can get a tertiary amine using this method. So again, all of these can be used to form these three different methods. The sodium azide, as well as the Gabriel synthesis, can be used to form primary amines. Reductive amination, you can also form a primary amine, but even more flexible is you can do reductive amination on a primary amine to form a secondary amine. If you do reductive amination on a secondary amine, you can form a tertiary amine. And then we learned about that alkylation method, which always forms the quaternary ammonium ion. Okay, other reactions of amines that we talked about are amines reacting with acyl chlorides to produce amides. Remember that you need 2 moles of your amine because the hydrochloric acid that's produced will want to react with that basic amine. One good reason why you might do this is this over here would not be basic. So it would not be in a position to accept a hydrogen. One reaction that we haven't learned about, we've learned about it plenty, but not in the context of amines, are elimination reactions, right? So we've talked about alcohol groups and how you can do an elimination and get to an alkene. Remember how we do that is we first protonate it. So have some acid present in order to protonate that and thus make it a better leaving group. That would be one method. So similar when we want to do an elimination reaction with an amine, we have to consider the fact that this will leave as an amide ion, which is a terribly strong base and thus a terrible leaving group. So what do we do? Well, we can use this method that we sort of learned about before, which is the alkylation. And what that does, by adding an excess of a very tiny alkyl halide, right, something that's going to be susceptible to SN2 type reactions, we can form this quaternary ammonium ion, and this will leave as a tertiary amine, a much better leaving group or weaker base than an amide ion. Okay, so that's what we got to do first if we want to do elimination reactions, is first have excess of an alkyl halide, convert it to that ammonium ion, which will be a better leaving group. And then in order to do the elimination, normally we would just use a base, right? Like sodium hydroxide or something like that. And that will work. With amines in particular, I don't even know why, but silver oxide is the sort of preferred way to go, okay? I don't even know exactly how that reaction goes in terms of mechanism. We don't have to worry about it, but that's what silver oxide is doing here, is basically acting as a base, okay, in this elimination type reaction. Again, we can use another sort of base. The reason, the ACS, if they do have this reaction, they will have this silver oxide sort of thing. In terms of mechanism, we can just think about it as if it was a normal base that we're used to, like the hydroxide ion. And that, of course, has this E2 type elimination reaction, meaning that everything happens in one step, right? The base grabs the hydrogen, the bond from the hydrogen carbon comes down to form a double bond, and you have your leaving group leave. If you're sort of remembering your E2 reactions, you would say, well, hydroxide's a small base. Why do I have my double bond there instead of having it here, right? Normally, the formation of the more highly substituted alkene is preferred. Those are the more stable in terms of free energy. This is what's called a Hoffman elimination, meaning that it goes on the less highly substituted carbon, or the terminal carbon, okay? You form the less highly substituted alkene, which we generally think of as being less stable. So why is that? Bottom line is it has to do with the fact that this quaternary ammonium ion is a very bulky leaving group. Most leaving groups that we have are not big and bulky, so we don't really have to consider the sterics of the leaving group very often. In this case, we do, because it's a particularly bulky leaving group. And so the bottom line is, if you remember in E2 elimination reactions, you have to have your leaving group in the same plane as the hydrogen that's being plucked off. That's what's required for an E2 elimination. It's what made the stereoselectivity of those type of elimination reactions a pain in the butt. So the problem is that if you try to remove the hydrogen from carbon 3, which would produce your more highly substituted carbon, your big bulky leaving group will form a gauche interaction with the back half of that alkene. All right, so this would be this chunk right here interacting with this chunk right here in terms of steric clashes. If you pull it off the terminal leaving group, again, we have our ammonium ion in that same plane as the hydrogen that's being removed. Notice that we avoid those sort of gauche interactions in this rotational conformation. So long story short, the Hoffman elimination, or forming the less highly substituted alkene, which isn't what we expect normally. In this case, that's what happens when nitrogen is the leaving group in the elimination, or more specifically, that quaternary ammonium ion is the leaving group.